Welcome back, ladies and gentlemen.
Welcome.
So we got another episode for you today with some pretty fresh, relevant news. But first, guys, make sure you like, share, comment, and subscribe to the channel if you haven't already. And check out the website, Eigenbros.com. Check us out at Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros2 on TikTok. And also, thank you to the patrons once again. We really appreciate you guys. You know, we appreciate all the support. And if you guys want to check us out on Patreon, we've got more fast and loose episodes. You know, we've been hearing from you guys. You want to hear more the personal side of the Eigenbros. So, you know, check out Patreon if that's an incentive for you. It's patreon.com/Eigenbros.
Yes.
Let's get to it.
Please check that out. Yeah, this week, breaking news. Test of Lepton Universality in beauty quark decays from the LHC.
And what does that mean? Just kidding.
It means what it means. Nah, it means it means we don't know jack about the universe. Nah, there's an incongruence found, I guess, right?
Yeah. So yeah, this was breaking news about what? As this podcast comes out, I guess 2 days ago.
Yeah.
So yeah, they had some interesting results from the LHCb. That's the Large Hadron Collider Beauty. That's a one of the sub experiments in the CERN facility, on the France-Switzerland border.
Yeah.
That you all may be familiar with, the whole God particle situation. So that's the same place. This is just one of the other smaller experimental setups that they have. It's one of the larger ones of the smaller ones. But yeah, it's another synchrotron facility, and they were probing some new physics, or they were probing some things, and some new potential physics might be happening.
Yeah, I mean, as far as CERN publicly announcing something, they've stated that if this...
Oh, by the way, did you have my notes pulled up one? Sorry to interrupt. Okay.
If this were to be confirmed, it would suggest a hint of the violation of basically the standard model as we know it, particle physics.
Yeah, it's a big violation apparently. Of course, to put a little caveat again for the audience, me and Juan are not particle physicists.
No.
This is pretty much out of our area, so we don't really know shit. We know the general side of physics, right? So we can probably maybe add more than someone who's... if you're a layman, you'll probably get more out of this. If you're a particle physicist, you might just be
you might
raging
hear the
at us.
introduction and be like, what? And then actually go check the source yourself.
Yeah.
But
it's probably not going to be super useful for you.
If you're a particle physicist, you would not be hearing from us. If you're hearing from us...
So we give you permission
to... bad.
Yeah. That means you're just looking for some entertaining
yeah, exactly.
science content or something.
Right.
Yeah, we're not going to be giving you any real grand details here, let's say. So
but as a famous news website goes, very reputable news site, wink wink, says, we report and you decide. Anyway, the results focus on the potential violation of lepton flavor universality, and it was announced on the Moroin.
Read my notes, Juan. I have it all
Gotcha.
synopsized there.
Yeah, Terence has got points, but
well, if you read the synopsis, it basically shows you those
gotcha.
paragraphs in the article.
See, Terence made it beautifully succinct for me.
I'm trying to get better at making the notes understand.
On Electro Week, interaction and unified theories, and an online seminar at CERN, the European Organization for Nuclear Research basically reported this, and the LHCb compares to two types of bottom quark decay.
Yes. So they call it beauty quark. Some of you may be confused with what the hell, beauty quark versus bottom quark, if you read the article. I was. But I remembered from the past when I took nuclear way back when, that the beauty was the first name, but then they decided to go with bottom quark. And I guess it's just for the dichotomy of the top versus bottom quark. I don't know why, but yeah, so it's and the thing is, it's a little bit confusing because it's B mesons. B plus mesons that were actually the real decay. So they were looking at B plus meson decay. And I guess they call it beauty quarks because the beauty quark the B plus meson is a combination of the beauty quark or the bottom quark and an up quark.
Yeah.
So I guess the beauty is just the most significant part of it, or the bottom quark. We should probably call it bottom quark from now on, because that's the standard terminology.
Yeah. And
I have links in there too if you're trying to wonder what the bottom quark is or something.
Yeah, because they have you could just if you're kind of a casual particle physics person like me, you can easily Google like the particle physics diagram on Wikipedia.
Yeah, just type in standard model.
Yeah. Standard model?
Yeah,
Bro,
standard model is what it's called.
Dude. How dare you call her a standard model?
She's a bit derivative.
She's gorgeous. Nah, but like I guess for those not in the know, should we kind of go over there's
Sure,
a lot of,
you can go over it
our
briefly.
audience is mostly, I believe, not nuclear. Right?
Our audience is probably mostly undergraduate.
Yeah.
Well, maybe not though. I mean, we look at our demographics and we're like we're in the like 20 to 35-year-old camp, which I would imagine is like late undergrad, mostly graduate. So I guess we have a mostly graduate audience. Well, so they're probably here more for the entertainment than the actual knowledge.
So, but it's still, nevertheless, if you're not really into particle physics, quarks, we have like four subtypes of particles, right?
Yeah.
We have the quarks, the leptons, the gauge bosons, and then the solar bosons.
Solar?
I mean, scalar bosons. Sorry,
Juan, you got me questioning my knowledge now.
I saw yellow and I was like, solar. I am so sleepy. Scalar.
You're that guy who thinks that electrons always got to be blue and protons always have to be red.
Yeah. Thank you for exposing me like that. Scalar,
I am too, Juan. Don't worry.
Scalar bosons. They're scalar bosons. Scalar bosons, unfortunately, population of one. Because it's the Higgs.
Right.
The Higgs
and it's
mechanism.
scalar because it has a zero spin, I believe.
I see.
Correct?
You're telling me, dude.
Oh, I don't know.
Quarks. let's suppose.
Doesn't it have or does it have a
Oh
zero
yeah,
spin?
Higgs has a.
It's the only. It should be the only one with
it's
zero
neutral.
spin.
Yeah,
okay.
yeah.
But
the quarks, they're up, down. They're the most famous ones. Well, not the most famous, but in terms of particle physics, they're the weird ones that you didn't learn in elementary school.
Which one?
The quarks.
Yeah, but the up and down quark are probably the most pedestrian of the ones if you do know about quarks.
Yeah.
Right, because the up and the down are the ones that compose pretty much the elementary particles we're familiar with.
Yeah.
Like protons and neutrons. Protons are two ups, one down. Neutrons are two downs, one up. And then, of course, the up quark is a positive 2/3 charge, and then the down quark is the negative 1/3 charge. So if you add that together with the two ups, that's 2/3 plus 2/3 is 4/3.
Yeah.
Plus negative 1/3, which is just 1, which gives you a total charge of 1, which is why the proton is a plus 1 charge. Anyway.
Yes.
Continuing on.
And the same thing with the charm. So we have the charm and then the strange.
Right, and this is the second generation of matter. So this is just saying now these are the ones that are a little bit more mysterious and strange. These are the ones that occur at higher energies. So you're not going to see these really in nature. This is like kind of a product of laboratory equipment and testing.
Yeah.
So the charm quark and the strange quark are the second generation of matter that's heavier versions of the up and the down quark.
Yeah, and they still have spin 1/2, I believe, and then they have a charge of. I think the charm has 2/3, and then the strange has negative 1/3.
Right.
Strange.
So you see that's the same as the down quark and the up quark.
Yeah, it is.
Except they're just the heavier version.
Yeah, heavier. Well, we don't body shame here, so.
Big particles need love too.
Yeah, big particles need love too. So, generation 3, we have the top and bottom.
Right.
By the way, they really should have thought of some kind of. What is the word, like lexicon? Like they should have had a better scientific naming scheme. Like physicists, they're not like biologists where they get they talk about they're like we should introduce Latin into, like our schema of naming things. They're just like I don't know up and then you have top. What the
probably because up was already taken, so top I guess.
Well, what's in that? Well, yeah. What's something?
My mom's calling.
Yeah, why would you? Why? I don't know. This confuses me as someone who's not in particle physics.
Yeah. Maybe the naming will make more sense if you actually were in particle physics, but As far as I know, I don't know.
Yeah. Teaching this to a child, I think, would be very confusing.
Yeah.
But anyway, so then you have the top and the bottom in generation 3. And in a similar fashion, they also have, the top has 2/3 charge, and then the
Right.
bottom has negative 1/3 charge, and then they both have spin 1/2. So
Right. And these are the most fundamental particles in the universe,
Yeah.
basically.
So yeah, and these are like, I mean, there are two categories. It's fermions and bosons, and the fermions are mostly what make up. They call it the matter stuff, I guess, the generations of matter.
Yes, exactly.
Yeah. So like in the category of fermions, you had I guess specifically the quarks and the leptons, and so we just talked about the quarks, but now the leptons, they're the more famous ones. You have the electron, classically, with a -1 charge, and then that's probably the most famous one. And then you have the muon, which is also -1, spin 1/2, but it's a lot more has a lot more mass. It's a lot heavier than the electron. And then
I think
you
it's
have,
about 200 times heavier than the electron, I want
it's
to say.
huge. And then but it still passes through you. You ever think about that, dude?
Oh, shit. Scaring me, Juan.
Yeah, it's phasing through you. It's phasing through you right now. So,
Yeah, we actually have, I think muons are the predominant particle for cosmic rays, I want to say.
Yeah, they are. Yeah, but the last one is, well, not the last one, but the more common one is the tau, the lepton, and it's
The
also
more common one?
Yeah, like in terms of I knew about the tau one.
Bro, that is not common.
That's
at
not
all.
common. Okay, well, I guess
The tau is probably the most uncommon lepton there, right? Because any of the third generation
the newer
particles
ones you're
are
saying?
always the way heavier ones that
Yeah.
only exist at high energies.
High energies, yeah.
Right? The electron's by far the most common one.
True,
right?
true.
And the electron, muon, and tau, actually, this is kind of relevant for this whole violation of the flavor stuff going on. The electron, muon, and tau are all pretty much identical. The only difference between them is the mass. But they have the
Yes.
same kind of interactions. They have the same spin, same charge. They're virtually identical, which is
Yeah.
why they're all kind of grouped together in this whole category called the leptons.
Yeah. I mean, to kind of give you that introduction, yeah, and then I guess just to give you the rest. I mean, the other leptons are the neutrino versions of those.
Yeah.
Yeah.
And those were created for momentum conservation or energy conservation because they noticed that, there's missing energy or momentum or something after these collisions. So they added in the neutrinos as a correction factor.
Yeah.
And then it turned out that those were actually real.
Yeah, and these are pretty much the standard. This is kind of the standard model for the fermions.
Yeah.
The bosons, I don't think have anything to do with this particular study, right?
Somewhat.
Somewhat? Oh,
because it's an electroweak violation.
Oh, true. Yeah, and this is why it's important, I guess, to talk about the bosons because they're technically the force carriers.
Yeah.
They're the
Which I always
interaction
thought was
carriers.
confusing. Did you ever wonder why are those forces?
Yeah, I know.
I actually was kind of thinking about that the other night because I was like, and I realized that it's just because they realized that there has to be some kind of exchange of information to convey a force on something, right? So they filled it in with particles because we just noticed that, during the late 1950s, I want to say early 1960s, there was the whole particle zoo. They're just thinking like, okay, we just have everything's a particle, right?
Yeah.
So it was a guess that potentially that these other particles or forces are mediated by more particles, right?
Yeah.
So then you wonder like, okay, like how do you really know that? But I guess it's just that once it was confirmed experimentally, then they were like, okay, it actually is a force carrier. But it's interesting because I guess it's not so much that because we know that the electromagnetic force actually has a push or a pull on something, right?
Yeah.
The other ones that you'll probably will talk about here in a minute. One, it's like the gluon and the
photon, the bosons.
The photon's the standard one that conveys the electromagnetic force, right?
Yes.
So we know that one actually has a push or a pull. So then we call the gluon and the W and Z bosons force particles as well, I guess, because those also are spinless particles or integer spin particles that have the similar properties as a photon. So I guess it's all kind of hinging on what the photon does. The photon is a force that we see that actually pushes and pulls on matter. So they're extrapolating that same understanding to the gluon and the W and Z bosons.
Yeah.
Not so obvious. I didn't know if I really even liked that.
No,
explanation,
I think it's a
but
decent explanation.
But yeah, it's like it's not so obvious why they're forces per se, but it's just because they have certain properties that also the photon has.
Yeah.
Long story short, so it's like
Pretty
you
much.
call those force mediating particles as well.
Yeah. Maybe text Andrew. You know, have him on the
Andrew. Oh, Andrew. Yeah.
On the-
Andrew Dodson.
Yeah. Have him on the line. Just be like,
Yeah.
let's ask you a question real quick.
Right.
No, but
I wish we had Andrew on call like that.
But in theory, decay rates among so going back to what we were talking about in terms of this whole study and what it means, the LHCb compared, like we were saying, two types of bottom quark decays. The first involved the electron, and the second involves the muon.
Right.
What did that mean? I guess I was kind of curious. Like, what did you take away from that?
Yeah, so I was talking a little bit earlier about the B plus meson, right?
Mm-hmm.
So B plus meson, a meson is basically okay. So there's these things called hadrons. To let me start. So hadrons are basically composite particles. A hadron would be a proton because it's composed of quarks.
Yeah.
So if you're composed of more than one quark, or even, I think maybe even a lepton. No, I think only quarks. So if you're composed of more than one quark, you're a hadron.
Mm-hmm.
So you can be composed of 3 quarks, or you can be composed of 2 quarks normally.
Mm-hmm.
Of course, there's some weird shit out there like tetraquarks and whatnot, but we're not going to get into that.
Yeah.
So the standard hadrons are 3 or 2, right?
Yeah.
So mesons are 2, and then baryons are 3.
Yes.
So the particles that they looked at in this LHCb are the mesons, the 2.
Yeah.
So a meson is composed of a regular particle and an antiparticle.
Yeah.
And in this case, they were looking at decay reactions, electroweak decay.
Mm-hmm.
So what happens is they send this B plus, or they collide 2 protons together, basically at really high energies. Of course, high energies can be converted into mass, right?
Mm-hmm.
This is one thing that Einstein found out. E equals mc squared, the classic. Of course, that's not the full version. It's E equals mc squared
Plus p term plus
plus
momentum
PC.
terms. Yeah.
I forget what the fuck it is,
Plus
but
other
look it up.
Plus other momentum terms. Yeah.
Yeah. We'll put it on the pod the YouTube. But anyway, that energy from that
Energy conversion.
conversion from those proton collisions will turn into B plus mesons, or potentially it could. So they look at those B plus mesons and they look at how those decay over time, and those B plus mesons will decay into a kaon, which is a type of particle you may not be familiar with. This is one of those particles that's in the particle zoo, right?
Okay.
it's another type of meson.
Oh, gotcha.
So it turns into a kaon as well as 2 leptons.
Yeah.
So it's the positive lepton and then the antiparticle version of the lepton. So for instance, it can turn into a kaon and 2 electrons, an electron and a positron.
Yeah.
Or it can turn into a kaon and 2 muons, a muon and an anti-muon.
Gotcha.
So this is just the 2 versions of this particle decay for the B plus meson.
Gotcha. Okay.
Yeah.
All right.
So that's what they're looking at.
Gotcha.
And then
Okay.
with those 2 different ones, there's some violations that can occur. And if you actually want, it might be good for you to download the paper. I actually sent you the paper. Okay.
Okay, cool.
Yeah, so I mean, I skimmed over everything because it was just like, I mean, this literally just came out yesterday, I guess.
Yeah.
I mean, for us,
Yeah.
it's quite shocking because in theory they say the decay rates among different lepton flavors should occur with equal probability, and the results show there's like a significant deviation from this. In fact, basically 3 standard deviations away from what's expected.
Yeah, exactly.
Yeah.
So that means a 3.1. I think I have a link in there related. One for standard deviation if you want to look at the chart.
Yeah.
But for 3.1 standard deviation, I believe is a 0.1. It's around a 0.1% chance that it can align with the standard model. So you see that's a 1/10% that it's going to align with the standard model. So it's a bad news for the standard model, right?
Yeah.
The evidence don't lie, right? Unless you're fucking up your experiment somehow. But this is interesting because they also say that this has been going on for
Yeah.
at least a decade or something now.
Deviation is consistent with the pattern of anomalies observed in related experiments globally over
Yeah.
the past decade. Yeah.
So that's an interesting thing. I mean, I wouldn't be too worried about the standard model because the standard model has lived up truly to itself. So to multiple tests of scrutiny and everything. So
Yeah.
this is more exciting to say that there's some new physics potentially that exists now.
Which is good.
Yeah, so this is a job, right?
Yeah. Exactly. Calculation of standard model branching fractions is complicated due to the strong force. This is what
Yeah, so we can. You should open up the paper now if we want to talk about this. So the branching fraction is really kind of go to page 1, I think.
No, I'm here.
It's labeled page 1.
Oh, literally page 1.
Yeah, and look at the image.
This one here. Yeah, so
this is basically what I was describing to you, Juan.
for
You
the
can
audio
see,
listeners, rest in peace.
well, maybe you can describe what you're seeing here, Juan. So
We got some Feynman diagrams, essentially some loop diagrams, and it's basically showing the contributing to these B plus mesons, how they're generated, and these K plus particles are also created. I would go ahead and go look for the paper if you're really interested, but we're going to skim over the details here. The paper itself is called Test of Lepton Universality and Beauty Quark Decays.
Yeah.
So
it's also one of these papers that has like 900 authors on it.
yeah.
Because all these LHC papers are just every single person who worked on the project, right? So it's just a fucking giant swath of people who are on the author list.
I wonder if
so you should see it as a highly cited paper. I would imagine soon.
That's impressive. Like, imagine you just like you work at the LHC, but like maybe as like a lowly engineer.
We're like the janitor.
Yeah, I was part of that team.
Yeah,
I was part of the team. Hey, bring me on. I would love to do that kind of stuff. That'd be cool.
But anyway, so the branching factor, right? You were saying the branching fraction.
Yeah.
They call it a few things: branching factor, branching fraction, branching ratio, whatever the hell. So what's going on here, Juan? If you look at that picture again, you can see this is what I was describing to you with the B plus meson.
Yeah.
The B plus meson's composed of an up quark and an anti-bottom quark, right? Mm-hmm. So if you remember the bottom quark when you were looking at the standard model earlier, it's a minus 1/3 charge, right?
Yeah.
So then the anti-bottom quark is going to be antiparticles are basically all the quantum numbers reversed.
Yeah.
So instead of a negative 1/3 charge, it's a positive 1/3 charge, right? And then the up quark is a 2/3. So the B plus meson, or the charged B meson is what they call it as well, is the +1 version. That's not a charm version. Okay, I'm kind of getting a little bit. This is the shitty thing about explaining physics. Sometimes there's so many like caveats and things because
this is why we do the math, man.
Yeah. So an aside is there's many different kinds of B mesons. There's instead of an up quark and a anti-bottom, there's always the anti-bottom, but there's different substitutions for the up quark. There can be the up quark, there can be the charm quark, and then there can also be the top quark, I believe, and maybe even. Yeah, I think that's what it is. But anyway, that being said, the two different versions we're looking at here is the B plus meson, and it decays into the kaon, of course, both times, but then it decays into either a positron and an electron, or it decays into a muon and then an anti-muon neutrino, or an anti-muon, not the neutrino. So if you look back at that image one, we've got the first version that includes the W plus. So this is the part where I kind of got lost a little bit.
Oh, this is above our pay grade here.
Okay. Damn, I was hoping maybe you could look at it a little bit because I know you did some.
Yeah, I did. I've done some diagrams here, but it's just
Feynman
showing
diagrams aren't that hard to read. It's just that I didn't really super understand this one.
It's just showing there are two different fundamentally, I would say two different mechanisms that are going on here to produce these two leptons, essentially.
Yeah.
And one of them gives you a hypothetical leptoquark.
This is the second one. This is the one that has the new physics potentially.
Yeah, this one, and that's basically it. I mean, the old model would try to account for creating a whatchamacallit, electroweak bosons essentially.
Yeah, so it makes it
Yeah.
makes a W plus and splits off into some kind of
Yeah, those loops are just
anti-charm or
yeah.
anti-top,
Yeah,
and
yeah.
then it decays into either a photon or a Z boson, right?
Yeah,
So it's like the electroweak force going on here,
yeah.
and then that decays into two electrons or an anti-electron or something. But then the new one, the weird one, is the one with the leptoquark. Because I looked
Yeah.
up the leptoquark. I even have it on the notes if you want to pull up what leptoquark is. But leptoquark is some weird hypothetical particle. I don't even really understand it per se.
Mm-hmm.
But if we have some particle physicists in the audience who want to correct us or add some information here, this is I think this is an important piece for really understanding the new physics going on here.
Mm-hmm. What, the leptoquark stuff?
Yeah, because it's like a weird new hypothetical particle. You can maybe read on it a little bit more.
Yeah. I mean, as far as like the literature is concerned, I guess it's pretty much they're a hypothetical particle that if they exist, they must be heavier than all the currently known elementary particles. And the current experiments lower limits on the LQ mass depending on their type are around 1 TE. Dang, that's huge.
Yeah. So it's tera electron volts.
Yeah, it's
right?
huge. By definition, the leptoquarks decay directly into quark and leptons or an anti-lepton, but they live for a very short time and aren't present, obviously, in ordinary matter. But yeah, so this is
Have you ever heard of leptoquark before?
nah, man, never.
Yeah,
No.
I never heard of it either.
They're supposed to be like color triplet bosons.
Yeah, this is where it starts to get complicated.
Yeah,
I'm
so
like, I
this
don't
is
know what
where
the
the
fuck this
actual
means.
like accounting comes into particle physics accounting, because they're supposed to carry a lepton and baryon, all this other stuff, and yeah, it's very detailed. But I mean, this might hint this basically they're trying to describe the data that they see, and they basically are trying to describe it using this idea of a leptoquark. Fitting the model.
Yeah, I think so. But I guess to go back a little bit, because I kind of forgot to address the branching ratio.
Yeah.
So the branching ratio is basically the ratio that it was saying that these interactions. So you remember I was saying there's the decay from a kaon into an electron and an anti-electron, or a kaon into a muon and anti-muon.
Yeah.
Those are supposed to give the same probability. So it's like there's something called flavor universality, apparently, in particle physics, where the reactions, when you look at the numbers, their probability or something should be the same. Like their probability number should be the same. But the thing is, so that's because if you look at the muon and the electron, they're the same in every way, right? What's the only difference between them?
Right.
It's just the mass.
Yeah.
That's the only thing. So at high enough energies, apparently, from the literature I read, they say at high enough energies, the mass is irrelevant. So then that means the probabilities for each of those decays should be exactly the same. So it should be, so the ratio between them should be 1.
True.
So then what they measured, though, the whole branching ratio thing, is the branching ratio showed that, or the branching fraction, whatever it is, showed that the actual probability was not 1. It was a different number than 1. So that indicates that now it's saying that there is a different probability for those decay rates or something. So that's where the physics is off now.
Yeah. This branching ratio is strange because it's like,
Yeah, this is actually kind of not my favorite wiki link either, because like I didn't know what it was really asking, and they also have an equation for half-life.
Yeah.
So I'm just like, well, I don't know what this is.
Why did they include the partial half-life? Why did they do that?
But I guess I can explain what, because I do have some other links in the notes one that are a little better for branching ratio. Look at the maybe decay modes, I think.
Sure.
Decay modes is a little bit better because it was showing, I was like, okay, what is a branching ratio anyway? And the branching ratio somehow it quantifies decay modes. So if you know, of course, Juan, there's different kinds of radioactive decay, right? There's the alpha particle decay.
Yeah.
There's like beta decay. And then there's like electron capture and things. So that shows all the different kinds of decay. If you see at the top, there's like the alpha decay, and then there's also the beta decay. So the branching fraction somehow shows you the probabilities for the different types of decay. So it's like, is this like, should this decay into an alpha decay? Should this do a beta decay? Whatever. And I think that number quantifies some of those different decay rates.
Yeah.
But anyway, that's like to try to give you an idea of what the branching fraction is. Of course,
Gotcha.
Again, disclaimer: we're not particle physicists, so I can't go super deep into giving you a great picture right now of what this all means. But this is just information for you to maybe piece together a little bit easier from what we've seen of what you can do with figuring out why this flavor universality was violated potentially.
Yeah. I guess they look at different types of because it says here that you have different. There are certain things you can measure, right? You can measure the half-life or measure these things that the lifetime of a particle. Essentially, you can calculate these things.
So I guess that's why half-life is relevant, because anything with radioactive decay is going to be relevant with half-life, right?
Yeah.
But like how it all ties together, I don't exactly know, right? I don't have a good synopsis yet. But so it's just interesting and I guess I should have defined flavor a little bit too, because flavor just means like it's just what type of lepton. Long story short.
Yeah.
It's just the type of lepton. Do you like a electron flavored? Do you like a muon flavored? it's another physics like a physicist's word, right?
So ridiculous.
It just randomly made it called flavor for some reason.
What's the flavor? I mean, this is so I don't know. I imagine every time somebody says flavor, I'm like thinking about that jingle from some 90s or 2000s commercial.
Which one?
Like, what's your flavor? Tell me what's your flavor?
Nah, is that?
I mean,
what was it on? Like what channel?
No, I mean, I don't know if this was a channel thing. This was just like a commercial, I think. I don't know what brand it was. Maybe if we find it, we'll put it on here. Like just as it'll awaken.
Maybe that could be the outro music.
It'll awaken something inside of you.
And nostalgia.
What's your flavor? Tell me what's your flavor. No, you don't remember this?
Nah.
Dang it. Maybe it was a Fanta commercial.
I remember one of
Doesn't
Fanta,
matter.
but that's all I remember.
Doesn't matter, but this just shows me that these particle physicists, they might be millennials, you know, if they know. But flavor's probably are old school, so it doesn't matter.
Yeah. But
I'm
anyway.
shocked. I'm shocked. I feel like, you know, as somebody who's not in particle physics, we have been led astray, run amok,
bamboozled.
They need to, you know, do a better job, please. The naming, this is so confusing.
It's just names, bro. What are you gonna do?
It's just names, yeah. I guess it's categorization, but I'm just like, there's got to be, you know, up, bottom, top, down. Nah, just give me better
skinny,
names.
round, short.
Just give me better names. Just give me better names, please. I really appreciate it though. It's really, really cool. I think they're onto something. In fact, it would be really, really nice if we don't figure this out, because there's a quote here you left. I don't know by who. It's
these quotes were actually just quotes from the article. They're not
okay.
anything like profound quotes. They're just in article quotes.
I see. Because it says here. No, we already said that. Yeah, it's just. I mean, I don't know. Just what was your take on it? How did the community feel about it?
It seemed to be big news, right? Because Dr. Brian Keating, you know, he's got a podcast. Shout out to him. He actually had like a live podcast the other day when it first came announced. I saw it on several people's timelines. I mean, that's the only reason why I paid attention to it, right? And it's a CERN announcement, so you know it's going to be a big deal, right? So that's kind of why, you know, it was even an indicator for me. I can't really say personally what it means because, you know, this ain't our field, right?
No.
But I can say it's definitely a big deal apparently within the physics community. You know, and physicists are always looking for new physics, right? Especially in the particle realm, because it has some direct usefulness in terms of like theories of everything and whatnot, right? Because literally the standard model Lagrangian was formulated with the different particles and their interactions involved, right?
Yeah.
So these things are very relevant to understanding the universe in its totality. But yeah, I mean, it seems cool, seems interesting. I don't really know much beyond what I've already said in the podcast, but yeah.
Really, I feel like you that's a lot. That's a lot of information, dude.
Well, I did a little studying.
Oh, okay. Yeah, but the field itself of particle physics is like incredibly rich.
Mm-hmm. Is this something I linked?
Yeah. This is like a like, I don't know anything about particle physics, but
yeah,
maybe for you folks that are intrigued about where the hell particle physics comes from. Essentially, there's like a cool CERN PDF that they released. It's very Star Wars-esque. Kind of
Is this CERN?
Very minimalist. Yeah. It's
I didn't even realize.
This professor puts this quote. It's like essentially 100 years of particle physics condensed into these slides.
Right.
But I like this quote here by Albert Michelson.
Yeah, you can say it either way. I've heard Michelson, whatever. I used to say Michelson, but I don't know.
Yeah, Michelson, 1894. I don't know if he said this that time or if he was born that day. Unclear. He said, all that remains to do in physics is to fill in the sixth decimal place.
It's one of these Lord Kelvin-esque quotes, right?
Boy, was he wrong.
But then apparently I heard that the Lord Kelvin quote was actually not true. So who knows what
did
these
Lord
guys
Kelvin
are saying.
say?
He was saying that all that has yet to be discovered has already been done or something, or I don't know. Something along the lines of like, we've already figured it all out.
He's like, yeah, you know what? I feel like, I love those people because it's always like, oh, I feel like I have a good enough understanding.
Yeah. But it's kind of, I think it's that one was just disingenuous to Lord Kelvin. He's probably in his grave, like punching the air right now because he's like, I didn't say that. You know, quotes go, people, and like people always regurgitate that Einstein quote of insanity.
Yeah.
It's like they pick the worst quotes from people. Yeah. I've always hated that. I know it's kind of random, but I've always hated that Einstein insanity quote. Yeah. And I also don't like the Lord Kelvin quote because I feel like he probably didn't actually say that.
Yeah. Wow, you feel like Einstein didn't say the true definition of insanity?
Because it's like, what does it mean? The definition? Because people love to just say anytime something insane happens, they just say the definition of insanity is repeating the same thing over again. I'm like, no, that's not the definition of insanity.
Of stupidity.
Huh?
That's the definition of stupidity to me.
I mean, not even that. I'm just like, that's not... Insanity and stupidity have nothing to do with repetition.
Oh, I see what you're saying.
It's just like it's just a dumb quote to me. It's like, fine.
That's fair.
Anyway.
Okay, so like, I mean, this basically goes over all the particle physics stuff here from... Actually, this chart is very difficult to read.
Yeah, actually, the one I really was interested... The reason I got this, because I was really interested in this part, the particle zoo. Yeah. Because I was trying to think of like, when did we actually start figuring out all this shit with the standard model? Like,
yeah. Well,
why did they even come up with that?
Okay, I'm understanding what this pictograph is trying to say.
Okay,
now.
yeah.
So now looking, we'll put it on the podcast probably for the viewers. But on the left-hand column, you'll see particles, and then in the 1900s, the first one we discovered was the electron. Mm-hmm. Well, that's disingenuous because really it was the photon, right?
The photon was way later, bro.
What are you talking about?
How would we discover the photon?
Young's like double slit experiment was like from the 1800s. How is that not included? Oh yeah. They did include it. Sorry, they just included it in E&M.
Okay.
Yeah. I don't know why.
But was Young's double slit before the electron?
Yeah. Yeah, I don't think they knew anything about the atom, dude. Oh, because you're saying electricity? They probably didn't know it was from the electron, though. You know what I mean? I think they were.
No, I'm thinking of Millikan's oil drop, though. Yeah, it seems like a way, huh?
That's like in the 1900s.
For real?
Yeah. I believe
so. You're saying photon was discovered first?
I must say yes.
The thing is, maybe if the concept of photon was known better, but I don't think.
Yeah.
But how would they measure the photon?
Corpuscles, bro.
But they couldn't get single photons, probably. How would you get?
For sure not.
So that's what I'm thinking. I'm like, because the thing is, you could get single electrons, right? Or no, you couldn't even. No. But you could get a better understanding of electrons, like with the Millikan, because he could actually measure the exact charge of an electron almost. or like not the exact, but we'll say a very good range.
Okay. Okay.
With the photon, though, like
Okay. The Millikan
They had a
experiment-
lot of debate with the photon.
They did, but the Millikan experiment was in 1909, and Young's double slit experiment.
I think if a better experiment one for photon would be the Einstein one, the photoelectric effect, because then you
Yeah.
can measure actual voltages per photon that leaves the metal plate.
Okay, fair enough.
So that's more reasonable.
But I mean, I'm saying that they figured out what the hell light. Well, I guess they wouldn't really figure out what the hell light is.
nah, that's Maxwell's.
But we started testing light, how weird light is.
Yeah.
In the 1800s, like 1801. That's when we started.
the double slit was
Yeah,
1801. Holy
1801.
fuck! I didn't know that.
Damn. Okay.
Yeah, dude, isn't that wild?
That is kind
We're
of
like,
wild.
what is this light shit?
Damn. These motherfuckers were smart, man.
Really? I mean, I would be like, if I saw light, I'd want to do the same thing. I'd be like, what the hell is this light shit?
Yeah, but I don't know if I would have thought of that.
Like putting. Let's see how it behaves when you
Yeah.
switch in it.
I guess maybe because you're like, how small can I get this? I don't know.
Yeah, yeah.
You can't say unless you lived
yeah,
then.
True,
you
true,
know?
true. Well, let's just say you didn't have TV, so you. Had to
True.
find
That
it.
would be.
Probably the only entertainment I have. I probably just play instrument or something though.
Yeah, fair. Yeah, probably. But anyway, the two particles that I think were all, I guess, fundamentally more, I guess, in tune with was light and electricity. Like, you know, electricity being electrons and then light being like photons.
Sure.
And then
both governed by the photon
yeah,
boson, the electromagnetic force. So
and then Fermi.
we really cracked the electromagnetic force way early on,
yeah,
right?
for sure. Yeah,
That's probably our most understood.
Area of physics.
yeah, big time. And then like in the 1900s, we pretty much started breaking down. In the last century, really, we started breaking down like or deconstructing like the atom.
Mm-hmm.
And then we got the atom, the nucleus, and then you get all your particles. Like, and by the time you hit like basically 1930s is when you start getting, you know, the positrons, I think,
Mm-hmm.
and then the neutrons, and then you get a decade later you get the muons, and then taus, and then all this other stuff. So basically around 1950 you get the particle zoo.
Yeah, that was really the big takeaway for me for this graph because I was like, you know, why all of a sudden did we start discovering all these particles? Like, why didn't we know about these before?
Yeah.
And then I realized, oh, it was because literally the synchrotron was invented in 1945. There's actually interesting story behind that because the synchrotron was invented like, you know, Leibniz and Newton both came up with calculus at the same time.
Yeah.
Two guys pretty much came up with the concept of synchrotron independently. So one guy in Russia, I think his name is like Vexili or something.
Sure.
He came up with the theory of it, and then another guy built it. I forget his name. I don't know. I probably have it in the notes.
He wasn't cool enough to be remembered. No, I'm just kidding. I'm kidding.
Well, he built it though. I think he was an American though.
I'm kidding.
But he built the synchrotron in 1945.
Yeah, respect.
So the synchrotron was able to output a lot more energy
Mm-hmm.
than the cyclotron, which was previous to it. So the synchrotron could actually sync up with the speed of the particles, or the magnetic fields. They said the magnetic fields could sync with the speed of the proton or whatever you're accelerating.
Yeah.
So it allowed you to have a lot more energy collisions, high energy collisions.
And that's why they were able to achieve the particle zoo.
Because basically when energy scales, right, that means the allowed particles with higher masses could also come out from that,
Oh, cool.
right? You can't see any particles with a certain amount of energy. So we were capped at the highest energies of what a cyclotron could do for a while.
Very true.
So once the synchrotron was invented, then it was like a whole nother world of particles that were allowed.
Yeah.
And that's when they found 150 new particles, and we're just like, wow, add it to the list.
Yeah. And then that's when the categorization, the hypercategorization of stuff had to happen. I mean, that's why I think you hear a lot of these like predicted things like the Higgs being like finally like
Discovered?
observed, I guess.
Yeah.
Because since the 1950s, they had been particle physics was like a burgeoning field essentially.
Yeah.
And so that's when you started getting all the people that were interested in it, started seeing all the data and tried to come up with basically models to try to fit it, or particles that might exist to fit that description. And
Right. They were just sifting through
Yeah,
massive quantities of data,
yeah,
right?
for sure.
And that's kind of nice because then they were able to put this really nice, succinct image of, okay, what is the commonalities between all these, between this particle zoo, right?
Yeah,
It's
yeah,
like, and then they figured out, oh, it's composed of these 3 generations of particles, basically.
Yeah, and by the time you hit like 1975 is when you get the first theorized, fully theorized, in its inception, standard model, like, which is kind of wild to think that was kind of, but that's probably the most accurate picture in terms of physics at the time.
Mm-hmm.
But in parallel, we had an E&M, I would say, or in fields, I guess, in governing like Maxwell's equation, electromagnetic fields, weak, strong. Those two are like, particles and fields are so basically married together. They're almost like you need them. You need them in congruence to really answer, to get a bigger picture, I guess.
Yeah.
Right?
And you can even say they're kind of the same thing. Like people in QFT have the models in QFT basically say that particles are just field excitations, right?
Yeah.
So.
Yeah, and it's I mean, particles and fields. I mean, that line kind of blurs with quantum mechanics anyway, right?
Yep, pretty much.
Yeah, and so
a little bit different though, because it's probabilities in some sense, but
true.
You're right.
But yeah, in 1950s you got quantum electrodynamics. You had like parity, charge parities, like those concepts introduced.
Right.
What it means to have like violations and whatever.
Right, you started getting these ideas of symmetry violations and these quantum numbers, like things like baryon number, lepton number, that kind of stuff too. Like these certain quantities that can conserved within all these reactions. Like, you know, I made a Twitter post actually recently on the conservation laws, and like basically all physics can be boiled down to conservation laws. Like if you just know that that energy is always conserved, momentum is always conserved, and angular momentum is always conserved. It's like 90% of like physics, really.
Yeah. It truly is.
It's just all the other stuff is kind of ancillary, right?
Yeah.
Physics is about conservation and symmetry.
Yes.
At the end of the day.
Yeah. Beautiful.
So
beautiful symmetry.
Mm-hmm.
But yeah, then you get in the fields, you get the Higgs field, you get GUTs,
grand unified theories.
Grand unified theories that are come out.
Yeah.
What do you think?
I laugh because I'm like, man, I can't. Whatever. I feel like we don't even have the whole picture, but good try. I'll give you a pat on the back.
Well, they've come out with the standard model Lagrange and whatnot, so
that's good.
It's on to something.
It's on to something. Yeah, I'm not gonna dog you for trying it, but I mean, go for it. Superstrings. Then we get like the idea of superstrings and stuff because of particle physics, and that all comes in the 1975. There hasn't really been like as much of a boom since the 1950s, I would say, since the particle like physics.
We could kind of think the LHC maybe because it finally put the stamp on the Higgs boson, right?
Yeah.
But in terms of like really getting new things, not much, right?
Mm-mm.
I think maybe tetraquarks were a new particle thing that was discovered. But yeah, I guess once the zoo was already discovered, they kind of already found pretty much most of the weird particles.
Yeah.
But I guess it's also why LHC is trying to crank it up even more energy scales, right? Because they want to see what else. But I guess it's like, at what point is it just we're just cranking up energy higher and higher?
Yeah.
Like before the returns are just basically nil,
diminishing.
Right?
Yeah.
It's crank it up to 11, dude.
That's what they're doing. That's what they're doing. So.
Yeah. I was gonna say I hope that it actually is a violation, because then that would mean that they had to revisit things. And, and then we might get new interesting physics, and then we might enter a different. Well, I don't know if this would create a whole different field, but like particle physics, but it might.
Do you think we could ever invent something better than the synchrotron?
Oh, you're saying with technologies,
so maybe some real new kind of way to crank up energy scales.
I don't know if going up to higher energy scales is like going to be.
That's not the way.
I don't know, because I think I don't know. I think Feynman had a quote on this. He was just like, I don't know if it's like what it might just go on forever.
Right.
It's like layers.
It's like layers of onions or something.
Yeah, yeah.
Feynman was the original Shrek meme.
He's like, it might just go on forever. You might just find particles and particles upon particles and never really gain like a bigger picture of it.
Right.
But I think
Particles are like ogres.
yeah, no, but it's like I guess I'm kind of, the amazing thing to me is that, yeah, I guess I didn't really connect the dots that the advancement of technology here, like the synchrotron, is kind of what helps develop certain like I guess probing techniques.
Yeah.
So I mean, yeah, that's something that we constantly like forget. Like technology and science are kind of, they run in parallel in terms of discovery, or discovering new things. So I'm like, yeah, we really, how do we I don't know. I'm just thinking, what's the next big thing?
Yeah, so you're thinking, yeah, so what do you think, Juan? What's the next technology that will enlighten us?
I'm hoping it's I'm just a condensed matter physicist, so I'm really, I'm a little biased.
We're a little biased, but I think
quantum
it's good.
computing, quantum computing for sure. And then even superconductivity.
Those are literally the two I was thinking.
I just hope like because like imagine the new physics that could come with. I can imagine like with quantum computing, you can start understanding. You can create different fields of, like not physics necessarily, but
bro, that would be so
biophysics.
wide-reaching,
Yeah,
right?
I know, yeah.
Literally everyone could use a quantum computer.
Yeah,
It would be a massive game changer, right?
Yeah, it would.
And literally the same with room temperature superconductors too, right? It's like not just the understanding of it. It's like if you could just use that in everyday applications for technology, like anyone could use that, and it would be so useful.
Using energy might be so cheap that it's going to be like, it's going to be not even a non-factor.
Right. We were saying that one of the big, one obvious real benefit to room temperature superconductors would be that, now you can have like wires and lines that stretch across miles and miles, and you won't need repeaters because the signal decay won't be as much, right?
Yeah.
You may need some things to clean up the noise, perhaps, but you wouldn't need it. You wouldn't have much signal loss. The integrity of your signal should last for a long time.
And that means that you won't lose as much to heat.
Yeah.
And you won't produce or generate a lot of waste.
Right.
It's a lot of.
It's like the ultimate wire.
Yeah.
The ultimate circuit.
And it might reveal something that we don't understand, right? Because like these are things that we don't understand about the electron. Like there's still so many things we don't. Like condensed matter itself, I like to think of it as like the study of the electron.
Pretty much, right?
It's like, how the hell does this one
how
fundamental
can we just exploit
particle,
the fuck out of this electron?
How does this one fundamental particle behave? Like, and that's, in a sense, we are particle physicists, Terence.
Yeah, we are. Well, almost probably at the end of the day, everybody's a particle physicist, right? If you look at it like that.
Yeah. No, but I guess we only focus on one particle. Is kind of the thing. Yeah, in terms of measuring like magnetic properties and electronic properties, like it really comes fundamentally down to how the electrons behave. But there are things that do in condensed matter. This is why you get a sort of intersectional play of particle physics, because you do get weird sort of what do they call them? They call them I'm blanking on the name. Pseudo like these pseudo particles, kind of
quasi particles.
Thank you. That arise, and this is like so prevalent in physics, but you have different types of fermions, like that they categorize, and even within like Majorana fermions, like
right.
Like we have our own categorizations of how electrons might behave, and we still don't really understand, like, I think.
Aren't Majorana fermions just basically antiparticles, though? What's the special property of them? I forget. I
think that they're.
The particle is their own antiparticle.
I believe
that's what
so.
it is. So I think all mesons are Majorana fermions.
I think I was just confusing it with something else. Yeah, you might be right. Yeah.
Check that, audience. Put a big caveat on that.
But anyway, Majorana fermions. Yeah, you have all these. I meant to say that just as like there are different things that we do also measure in condensed matter in terms of like the behavior of electrons.
Yeah. Yeah, we care about particles.
Yeah.
And we probably have the most quasi-particles, like you're saying. Like, I don't think nuclear physicists think about quasi-particles.
No.
I think they think about real particles.
It's
We
just
think about
weird.
Quasi-particles.
Yeah, it's just weird shit that happens, like, or that we still haven't figured it all out. And I guess in terms of particle physics, yeah, I guess I would like to invent this or help enable, room temperature superconductivity, quantum computing. I think those two things might open entirely new fields up. Yeah, so.
Yeah, those are two good answers, solid answers. I think those are probably, realistically, I think those are probably the ones that we should be looking towards. I think particle physicists have had their day. I think their time is now
going to be spent
Sounds
doing a
like
lot
a
of like
threat,
cleanup.
Yeah, I hope they cleaned it up because I hope the naming convention is also cleaned up because I think it's kind of confusing.
What would you rename?
Well, because the accounting is strange. Like, it's just, how do you? And I know there's never been a rebrand. Like, we won't even change the convention of the electron. Like, you know what I mean? Like,
Right. We just keep it as flowing positive. That's so ingrained in us, though. It'd be
it's
hard
annoying.
to change that.
No, you can change it in the next generation. I think you can. Like, you can do these things. It's just.
But then what about right-hand rule and what about the lenses law and all this stuff, man? It's too much. Lorentz force. We got to be adding negative signs and shit now.
Fair enough.
It's
All right.
annoying.
You're right. You're right. Yeah, man. It's just. Yeah, I mean, I don't know. Do you think?
What they should do is just make the electron a positive charge. And make everything else that's positive. Make everything that's positive now into negative, and make everything that's negative positive now.
They'll be able to do it in the future when everything is electronic.
Right.
All right. You figured it.
It's such a massive pain in the ass, though.
Yeah, I know.
I ain't learned it.
I refuse.
Yeah, but but I guess that would be my two, and I guess you're saying the days are numbered.
I think high energy physicists and particle physicists, I think they've done a lot, but I think they're not going to see as many high returns as are coming within the condensed matter field. I think condensed matter is really on the cusp of some really big shit.
Oh, for sure.
Yeah.
Yeah.
And I think high energy had that with like the Higgs boson, let's say, and even like particle zoo and all this stuff, the whole standard model regime. But I think their time is now kind of declining in terms of like big major discovery.
Yeah, they're tidying. Like you were saying, they're tidying things up.
Yeah,
They're
they're
cleaning.
putting bows on, they're dotting I's, crossing T's. I think that's great. Maybe something will give again later on and shoot them
So
back
you don't
up.
think you don't think this discovery is like gonna rock things up a little bit?
It could.
Yeah.
But even my first thought still would be that
The standard model is too good.
yeah, that maybe it's not going to really help high energy experimentalists and whatnot.
Yeah.
It might just help some kind of theorist, maybe a particle theorist or something, to figure out some way to fix an equation.
True.
I don't think many more new particles and things are going to really come about.
Gotcha.
Of course, this is all baseless kind of. This is all
Yeah,
just
but
me
it's-
basing it on what I think
you're
in
not-
a very
you're not
believy
gonna-
way.
Yeah, but you're not going to see an overhaul on something that already works pretty well.
Yeah, the standard model is so damn good, right?
Yeah.
That's the problem.
Yeah.
It's so good and so predictive, right? That it's like they're trying to look for any little crack in the system to find something new.
Yeah. Well, we'll see. We'll see. I don't know if you're in the field of particle physics, are there any kind of like giant things that jump at you that are just like still big question marks? I know when we were talking to Andrew, that particular question of what he studies is also it deals with nuclear, but
Yeah, it's really interesting because Andrew Dodson, for a recap for the audience, studies the spin of a proton. Like it's not really obvious that how the spin of the proton is going to be what it is, because if you add up all the spin components for the quarks that make up the proton, which is the up and down, it actually doesn't add up to what it should be. So it's kind of confusing. Which I think it should be a 1/2 spin.
Yeah.
So that's an interesting question, right?
Yeah.
It's really a deep question, and that can maybe give some insight.
Yeah. But it's a theory question. You're saying
Yeah.
it's like a theory question. It's like we have the data and now we have to align the theory to it.
Yeah, I think that the domain for the particle people is going to be maybe going towards theory.
Yeah.
The experimentalists are going to be more kind of crunching the numbers and cleaning some things up and whatnot,
Yeah.
kind of.
That's fair.
But I think for condensed matter, I think the ball is in the court of the experimentalists
It really
right
is.
now.
Yeah. Trying to figure out different setups or finding different materials that will give you the kinds of properties that you need to explore.
Right.
Yeah, this kind of tech.
Mm-hmm.
Yeah, I totally agree.
So yeah, any final thoughts, Juan?
No, I think that's it. I think that's a good ass summary. I think because I really didn't know that much about particle physics.
Did you take a class in nuclear particle or
never,
nothing? Okay.
Never, yeah.
What was your elective
In
in undergrad?
undergrad,
Yeah.
it was condensed matter.
Oh,
physics.
so not really so much an elective now.
No. That was my elective. Yeah.
Okay.
So,
Cool.
but yeah. But if you folks have any other questions that I guess you might want to alert the audience to, or even ourselves, in particle physics, like let us know. I'm super intrigued. Like maybe the standard model does have more holes than we
think. Yeah, because remember, guys, we are ignorant of particle physics because we are not particle physicists.
Yes.
So yeah, please enlighten us, and we will read the comments. So definitely leave something, and we'll respond. So.
Yeah.
But anyway, guys, thank you once again. Make sure to like, share, comment, subscribe if you haven't already. Check us out at Eigenbros.com, Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros2 on TikTok. And then thank you once again, patrons. And if you want to support your boys, check us out at patreon.com/Eigenbros. And I think that's it.
That's it.
All right. See you guys.
Later.